Hello everyone, my name is Bhargav. Today we are going to discuss assignment 4 of this course. Let's begin with the first one. The question says, in Deutsch algorithm, the first input register is in the question it is given that qubit x is combination of qubit 0 and qubit 1 and qubit y is given as combination of qubit 0 and qubit 1. And it is also given that f of 0 is 0 and f of 1 is 1. And oracle is defined as so the given input is which is product of these two qubits, which is so we want to find action of this oracle on this input. So what is the output when we have given x and y qubits to the oracle? The first qubit stays as it is and the second qubit changes. So is the first qubit stays as it is, the second qubit is 0. So in this case y is 0 and x is 0. So the output would be 0 XOR f of 0. As f of 0 is 0, 0 XOR 0 would be 0. Similarly, here y is 0 but x is 1. So 0 XOR f of 1. As f of 1 is 1, output would be 1. Similarly, for others, y is 1, 1 XOR f of 0. 1 XOR f of 1. Now let us look at the options. Option A says u of f is equivalent to where x operates on second register and I on the first register. We can see that the first qubit never changes, but the second qubit doesn't alter every time. For example, look at 0 1 state. It stays as 0 1 state. If at all x has acted on 1, it should have changed to 0. So option A is incorrect. And look at option B. Option B says x operates on the first register, but in the first state 0 stays as 0. So this option is also incorrect. And option C says UF is a C0 gate with first register as control and second as target. If we look at this state in this way, consider the first register as control and second as target. As the first qubit is 0, second qubit state doesn't change, it remains same. As the first qubit is 1 and second qubit is 0, we have as first qubit is 1 and second qubit is 0, as control bit is 1, target bit flips, so it is 1 1. Similarly, in every other state we can see the effect of C0 gate, so option C is correct. Let us look at question 2. In question 2, it says that everything is same as in the actual setup but the second output is changed to qubit 1. So the current input would be operating oracle on this input would result in this state, which is the first qubit stays as 0, but the second qubit is y XOR f of x. Y is 1, so 1 XOR f of x, that is complement of f of x. X is 0, so it is complement of f of 0. Similarly, the next state is now let us assume that f of x is constant. Say f of 0 equal to f of 1. Then output would be as f of 1 is equal to f of 0, we can replace f of 1 complement with f of 2, f of 0 complement, that is equal to as we know that Hadamard gate is applied on first qubit. In the next step, the output of the algorithm would be when Hadamard gate applied on this state, we obtain qubit 0. So output is qubit 0 in the first register. When we assume the function is a constant function, we obtain output as qubit 0. So if the function is a balanced function, there is chance that the output can be qubit 1. So we can clearly see that in case of constant function, we cannot have output as qubit 1 for the first register. So it should be a balanced function. Okay, look at question 3. It is given that input is a uniform linear combination of all states of 2 qubits. It is also given that f of 0 0 is 0 and all other possible combinations maps to 1. And we know that y is by input, I mean this is qubit x. So actual input to the oracle is this qubit multiplied with this qubit, and similarly every other qubit multiplied with the first qubit would be and now every qubit multiplied with the second qubit would be so this is our input to the oracle. Now output of the oracle is the first state previously is 0 0 0. Now as we know that the in the output the first two qubits are same, but the third qubit changes according to this function. We have here y as 0 and f of x, which is f of 0 0 as 0. So 0 XOR 0 would give 0. The second state is 0 1 0. As the last qubit is 0, that is y is 0. 0 XOR f of x would be stated as f of 0 1. F of 0 1 is 1. Similarly for other states, the actual state here is 0 0 1, but we have to replace with y XOR f of x. Here y is 1. So 1 XOR f of 0 0. F of 0 0 is 0. So it would be 1. Similarly for other states. So this is the output of oracle. We can write this into two terms, like observe these two terms. This can be written as qubit 0 0 times qubit 0 minus qubit 1, like qubit 0 minus qubit 1. Similarly, separating from other terms, we would obtain so this is the output of oracle. And now Hadamard gate is applied on first register, but first register is 2 qubits. So Hadamard gate in this case would be that is equal to 1 by 2 times 1 1 1 minus 1. This 1 multiplied with this matrix gives us 1 1 minus 1, and this number multiplied with this matrix gives again 1 1 minus 1. Similarly for other terms, but here minus 1 multiplied with this matrix will give, and this matrix is being operated on state which is the state present in first register, which is of first 2 qubits. This is equivalent to so this operator being operated on this state is equivalent to multiplying this matrix with this matrix. So the resultant state is this row multiplied with this column would give us -2. This row multiplied with this column gives us 1 plus 1 minus 1 plus 1, 3 minus 1, 2. Similarly, other two results would be 2 and 2. This gives us this is equal to, this can be written as half minus 1, 1, 1. The first term corresponds to 0, 0. And we can write other terms now. So the correct option is, now look at the options. The correct option is B. Now we look at question 4. The function outputs are f of 0, 0 equal to f of 1, 1 equal to 0 and f of 0, 1 equal to f of 1, 0 equal to 1. And the input is same as in question 2. So now we are directly writing the output of Oracle, which is the input is same as in question 3. This is the input to our Oracle now. Now we are writing the output of the Oracle. Now this can be written as two terms. Look at these two terms. We can separate them as similarly splitting all the terms we obtain now again we can split this term into two terms. Splitting these two terms, we obtain a term this. And now we can see that this would be minus qubit 1. Now applying Hadamard gate on the first two qubits would give us qubit 1, 1. We know that when H is applied on qubit 1, we obtain this qubit 0 minus qubit 1 by square root 2 as output. As H is self-inverse, when we subject this qubit state to the H operator, we again obtain qubit 1. As these are two qubits, when we obtain corresponding Hadamard gate on them, we obtain qubit 1, 1. So the output is qubit 1, 1, which is option D. Now we look at question number 5. In question 5, we are given a table where we have pairs of x and f of x. A table. In the question, we are told that if whenever we find a pair xy such that f of x equal to f of y, there exists a xi which forms a relation with x and y in this manner. To find out this xi, let us take any pair from the table. Consider input when input is 0, 0, 0, the output is 1, 0, 1. Consider another x where the output is 1, 0, 1. By looking at the table, we observe that 1, 0, 1 is also output for state 1, 1, 0. So now we have found x and y. Say this is x and this is y. We found an x and y such that f of x equal to f of y. So 0, 0, 0 XOR xi should give us y. Uh, Say this is symbol xi. So xi should be, and this y is 1, 1, 0. So the xi should be 1, 1, 0 XOR 0, 0, 0, which gives us 1, 1, 0. Similarly, if we take any other xy which gives the same output, we obtain the same xi. So the correct option is 1, 1, 0. So the correct option is 1, 1, 0, option B. Till now, we have looked at the first 5 problems where we have dealt some problems on quantum algorithms. Let us look at some more in the next video.